Hello everyone, welcome to today's session on a few processes to architect carbon. So I'm Rodrigo Martinez Duarte and I'm an associate professor in the Department of Mechanical Engineering at Clemson University. So what is today's talk about? So we will be addressing three different approaches to actually shape a polymer that we will carbonize. So the first one will be carbon MEMS or CMEMS, as you already know from previous sessions, which is the photolithography of organic resist followed by the heat treatment. In this particular presentation, we will be emphasizing the use of a photoresist called SU8, which is a negative tone photoresist, as you will find out in a few more slides. Then the second approach will be robocasting, or the use of 3D printing or additive manufacturing of pastes, followed by the heat treatment. And lastly, we will be learning about carbigami, which is the use of origami folding of films, followed again by the heat treatment to obtain the carbonaceous structures. So in general, the idea that we will be pursuing today is that we actually have a carbon precursor, as you can see there on the left upper corner in your screen. So we have a carbon precursor, and depending on how we heat treat it, it's the different kinds of carbon that we will obtain. So on the top route, for example, so you have the carbon precursor when you have an inert atmosphere and you heat treat it up to 1,000 degrees centigrade, then you're likely to obtain a glass-like carbon, right? Or sometimes called glassy carbon. So as you start increasing the temperature and you heat treat and even higher temperatures than 1,000 degrees C, then you can expect that carbon to start densifying. Sometimes, depending on the kind of carbon that you have or the kind of precursors that you have, you could actually aim for graphitization. But that's not always the case, and usually it requires very high temperatures. Now, you can also have the same carbon precursor, and then you can start adding fillers, like any of the many that are listed here. So you can start adding metals like titanium, silver, platinum, also metal oxides, other carbon allotropes, certain oxide compounds, or also biopolymers, right? So you will have these carbon precursors, you can add the filler, and again, depending on the atmosphere that you have during your heat treatment and the temperature that you pursue, then is the different kinds of materials that you could get. So up to 1,000 degrees C, if you have an oxidative atmosphere, you can aim for a metal or a metal oxide part, right? At those temperatures, likely the precursor, the carbonized, it also oxidizes. So basically you burned it, right? So you end up with the shape filler that you put in the system at the beginning. Now, if you change the oxidative atmosphere to an inert atmosphere, you can actually get a two-phase part material where you will have the carbon and then you will also have some derivative or even the actual filler that you put in at the beginning. I'll tell you more details in a few more slides again. And if you take that two-phase part material and then you keep heat treating it on different atmosphere, you can expect that you can also start getting carbides, carbonhydrates, and other materials. Right? So this will be the general framework of today's talk. So how exactly can we shape a carbon precursor? Sometimes we will mix it with different fillers, and then exactly how we're going to heat treat it in order to get different carbonaceous materials. And why do we want to do that? So here on the top you have polymer shaping, right? So we can actually have cellulosic paper, pastes, epoxy, different kinds of cellulose, right? A number of different organic polymers that it will actually lead us into carbon after heat treatment. So you can have the polymer shaping, then you can heat treat it directly, so you can start getting porous carbon. If you heat treat it further, you can start to densify that matrix. Now you could also have the precursor polymer. You can start adding a metal precursor solution, nanoparticles and else, such that you can have a porous two-phase materials. Then if you keep heat treating it, you can actually derive carbides. You could also have the polymer shaping. You can add epoxy, or you can have epoxy since the beginning. Then you start having a little bit more of a solid carbon, right? So it all depends on the kind of microstructure that you have on the initial precursor. What happens is at the very end, we will want to have a carbonaceous structure that ideally we can control the dimensions across multiple scales. Ideally all the way from the atomic scale all the way to the millimeter centimeter scale. And why do we want to do that? So basically we aim to have different architectic structures that they can be used as is, or they can also be used as skeletons for different composites. So imagine the carbonaceous skeleton that then you can infiltrate, you can coat with either polymers or a mix of metals. So you can see that core architected carbonaceous structure as the scaffolding or as a structure or as a base for many other composite materials, right? So that will be the general framework of today's talk. We will be addressing the different parameters of interest in the processing of these polymer precursors using different techniques. So the first major topic will be that of carbon MEMS, and especially through the photolithography of photoresist. So here you can see a few references where I base the following slides, right? There are many other references by many other groups. These are just a few selected ones. I will be providing references throughout the slides and also at the end of each major block in the presentation. So, photolithography of photoresists, right, or PR, followed by decarbonization. There are many different things that we can do, right, and that different groups have done in the last few years, right? So here you can see one common approach or one common objective is to actually get high aspect ratio electrodes that we use for multiple different applications, right? So people have used them for batteries, have used it for capacitors. I have used them for the electrophoresis, for example, in order to manipulate bio targets in a sample, right? So there are multiple applications for these structures. So also, another kind of geometry that you could get are those of suspended structures, where we can actually leverage the diffraction that can happen during the exposure of the photoresist, and we start having these suspended structures between these high aspect ratio electrodes or high aspect ratio structures that I was telling you before. Now, there are also some providers of functional SU8, just like a company called Gestaltech, where they actually sell you the SU8 that it's already functionalized with different particles. So for example, in the case of the left pictures over here, this was an SU8 that is functionalized with silica particles. After the carbonization, you can actually see the carbon matrix and the silica particles embedded in that carbon matrix. The one on the right, it's a SU8 that is functionalized with silver particles. After the carbonization, you can see on the back, you can see the carbon backbone that is decorated with silver particles. Now, we have also used this photolithography of photoresist for micromolding, where we actually use the process to create the structures that they're shown right here, right? So you can use different variables in the process in order to create multiple structures. I will tell you a little bit more about those. And lastly, we have also done molding, where we actually make these molds using micromachining, like traditional micromachining. We will fill the mold, and then after we will get these Lego-like pieces out of SU8 that then we will carbonize, right? So in the next few slides, in the next let's say 40 to 50 minutes, I will try to address the highlights of the photolithography process, right? So emphasizing some parameters of interest just as a short guide in order to get you started on how to optimize the photolithography process to fit your purpose. So, what is photolithography? So, as you probably know, you can have a negative resist and a positive resist. The following sequence of images, it will be focusing on the use of negative photoresist, right? So the first step is to actually coat a substrate. So here you have the substrate in gray, and we will actually coat it with the photoresist. Most likely spin coating, because that's the one that usually gives you the best results. After you coat it, you will actually have to soft bake it. So this is one of 2 bakes or maybe 3 bakes that you will actually do in the process. The purpose of the soft bake is to eliminate the solvent that allow you to actually do the spin coating, right? So after we soft bake, we should actually have a layer of only the photoresist. In that case, we will actually use a mask, basically a piece of material that it can be either dark or opaque to a particular UV light or a light of particular wavelength, that it has these opaque areas and these transparent areas. By doing that, basically you are selecting the areas that get exposed to that particular light of that particular wavelength, right? So one common wavelength is that of the eye line, or 365 nanometers. After you expose, in the case of a chemically amplified resist, like SU8, for example, you will actually need to incorporate something called the post-exposure bake. The post-exposure bake actually will provide that extra thermal energy that is necessary to finalize the cross-linking that you studied during the UV exposure. After that, it comes development. So the development, what happens is that you will immerse this or your device in a particular chemical, and that chemical will actually dissolve the parts that have not been exposed by the UV light. So those parts were not cross-linked, and they are more prone to get dissolved by that particular chemical, right? So after the development, you actually see the relief that you were looking for, and these will be shapes made out of the photoresist. So in the context of CMEMS, we will actually heat treat these parts after in order to transform them into carbon, right? So in a block diagram, the process looks a little bit like this. So you start with the substrate pretreatment, then you will do the coating. Sometimes you have to do something called the edge bead removal. So basically when you're doing the spin coating, you can imagine that the centrifugal forces, they will tend to disperse the photoresist across the substrate, but the meniscus that starts developing at the edge of the wafer, it will start holding the material down, right? So then you can start having some accumulation of material at the rim of the wafer, and that will be your edge bead. In most cases, you do not want to have this edge bead because that will have implications during the exposure, right? I will tell you a little bit more about those later. So after the edge bead removal comes the soft bake, then the exposure, then the post-exposure bake. Again, not all photoresists, they require a post-exposure bake, but SU8 does. Then you comes with the development, then rinse and drying, and then you have these 2 different options. Either you hard bake it in order to strengthen the resist, and this is recommended when you're actually going to use the resist as an structure, or you could also remove it after particular process. So first of it, so what is a photoresist? So a photoresist will be a polymer of a specific properties dissolved in a solvent. So think of raw honey, that will be your polymer, and how you will use hot water, that will be your solvent, in order to thin it, right? So imagine that you have the thickest honey that you can get, right? So in the terms of spin coating, that probably be difficult to actually have a nice uniform layer across a substrate. So in those cases, you may start adding some amounts of hot water in order to start diluting it and to start optimizing its viscosity, right? So as you can imagine, depending on the ratio of the photoresist, in this case your honey, and the hot water or the solvent, you can actually have a whole range of different viscosities available to you, right? So now there can be two major types of photoresist. That will be the positive and the negative tone. In the case of a positive photoresist, such as Shipley or AC photoresist, a particular light of a particular wavelength, when you expose your photoresist to that particular wavelength, what happens is that actually the polymer chains, they get cut, right? So they get weakened. So all these areas that will get exposed with the UV light, they will get weakened, so they will be more easily developed or more easily dissolved by the chemical that you use in the development step. By doing that, basically you will have a relief where the areas that get exposed to the light, they actually go away after the process. On the other hand, a negative photoresist, when you expose that negative photoresist to that particular light of particular wavelength, instead of cutting the polymer chains, you actually cross-linking you cross-link them such that you can actually have a stronger photoresist that it will sustain the attack of the developer at the end of the process. So practically what that means is that for a negative photoresist like SU8, the areas that get exposed to the light are the areas that will get or that will remain on the substrate after the process, right? So for the following slides, we'll be focusing on a negative photoresist, right? And it's particularly SU8, because as a community, we have been using SU8 for a number of years, and many works that are based on SU8. Other photoresists as well, like AZ and other positive photoresists, they also carbonize, right? So make sure that you check what objectives you have in your project, what kind of dimensions you're looking for, what kind of thicknesses you are looking for, because maybe in some cases the positive photoresist might make more sense than the negative photoresist. So always check. But for the presentation of today, we'll be focusing on SU8. And over here, you can see three major vendors of SU8. So you have Kayaku Advanced Materials. So these used to be Microchem, right? So Microchem now is incorporated into Kayaku. Another company is Microresist Technology, right? Kayaku, for those in the US, also sells Microresist Technology. And the last one over here is Gersteltech. So this is a Swiss company in Lausanne, right? And they in particular, besides the normal SU8, they also sell functional SU8. So you're encouraged to go and check the three of them and check what are the pros and cons for each of them. So besides the photoresist and the solvent that I was telling you about, you actually require a photoinitiator. So there will be three main parts of a photoresist. So you have the resist itself, like SU8, you have the solvent, and then you have the photoinitiator. So that will be the chemical that actually reacts to that particular wavelength and starts the cross-linking reaction in SU8 that you will later finalize with the post-exposure bake. Now, by changing the ratios of the resist to the solvent, you can imagine again that there will be multiple formulations. So both Kayaku, Gersteltech, Microresist Technologies, they have multiple formulations, and it all depends on the actual thickness that you actually want to get on your devices, right? So I encourage you to go and look at their websites and start looking at all the formulations that you have available. Now, so you have chosen your photoresist, right? So now the time comes to actually choose your substrate. So what kind of substrate do you have available? So since we're actually going to heat treat these devices to 1000 degrees C or 900 degrees C, high temperatures in an inert atmosphere, the first thing that you need to consider is whether that particular material will sustain that heat treatment, right? So that kind of limits our choice of substrates to silicon, the silicon that also it's coated with silicon oxide, right? You could also use fused silica. Some colleagues have also demonstrated the use of steel, right? We have also reported the use of ceramics. You could also have sacrificial substrates, right? So in some processes, we will actually do our photolithography process on a thin film of polyester or PET, right? So after we do the process, we will actually peel that PET film out of the SU8 structures, such that we only carbonize the SU8. We do not heat treat the PET. But in those cases, you can imagine that you can have different substrates where you can do your process, and at the end you can either etch the substrate or you can mechanically remove it, right? Sapphire, it can also be another option, right? The thing with sapphire is that it might tend to get expensive, but always check what kind of materials will sustain the high treatment, the high temperatures that you need for carbonization, right? And also, you also need to make sure that the photoresist that you're using actually will stick to that particular substrate. So in most cases, you actually need to do some substrate pre-treatment, right? So that brings us to our next slide. Let me go to this one first. So the very first thing, remember, you had to clean your substrate. So there will be different ways to actually clean the substrate, right? So it can be a whole hour by itself, just talking about cleaning the substrate, but here are a few highlights, right? So the most mild will be the use of solvents, right? So acetone, IPA, then you can start going into more drastic treatments like the RCA1, RCA2, Piranha, Aquarilla, and a number of other known chemicals or known mixture of chemicals in order to clean your substrate. Right? You can also have oxygen plasma. You can also have supercritical cleaning. Now, for some processes, you also require to do the dehydration, right? So that will be convection oven at around 200 degrees C, right? In order to eliminate any water residues and prime the surface for the coating. Now, going back to the slide, going back to the previous slide, basically it was mentioning about the choice of the substrate. So basically mentioning that you had to consider what are the differences, the coefficient of thermal expansion between your substrate and the SU8 or the photoresist that you're actually trying to pattern. And also the difference in the coefficient of thermal expansion between the substrate and the material that will get developed during the heat treatment, right? So the SU8, it will slowly morph into carbon. So those intermediate materials will have different coefficient of thermal expansion that it might also impact the addition to the substrate itself. So always consider those differences, right? And try to have coefficient of thermal expansions as similar as possible in order to prevent drastic deformation of your structures. Now, after you have identified your photoresist and your substrate, then it comes the time to coat the substrate, right? So you are trying to get a thickness that has a specific value, and that value is so uniform across the entire surface area or your substrate. This is important because if you don't take care of that uniformity across the entire substrate, you can start having some areas where your pattern worked, but some other areas where it didn't work, right? So always take care of that. Now, there will be different ways to coat a substrate. The most common one will be spin coating. In this case, you actually have a setup that looks like the one on your left, where you have this vacuum chuck. You will put your substrate, it will get secured to the chuck by vacuum, and then you will start depositing the photoresist that you're interested on, and then you will start spinning them, right? There are different spin coaters available. You can go all the way from very basic models, right, just a few $100s, to more complicated models that can go to the tens of thousands of dollars. All that will, well, your project will specify what kind of spin coater you will require, as I will tell you in the next slide. So over here you have 4 different examples of spin coaters, right? Some of them, they also have manifolds in order to allow you to deposit your material, right? In some other ones, it can just be as basic as just manually pouring your material in. Now, there are a few key parameters that you need for spin coating. So the first one will be the speed. So how fast are you going to start spinning? The acceleration, right? So how fast can you get to the speed of interest? The time of the coating, the topography that you might have on your substrate. You can have a flat substrate, a pristine substrate, or you can also have a substrate that is already have some structures on it, right? You also depend on the viscosity of the resist. Remember, that will be the formulation that you get from the different vendors depending on the solvent to resist ratio, and also you depend on the environment, right? So the environment around the substrate during the actual process. So for example, in the table in the right, you actually have different formulation of SU8. These are the formulations from Kayako, or they used to be Microchem, right? So here you have SU82. So you have different viscosities, and also recommend the spin speeds and for the thickness that you will will be attempting, right? So you have SU82, SU85, SU810, SU825. So as you see, as the number increases, right, the viscosity will start increasing, and also meaning that you will start targeting thicker layers. Now, another way of looking at this information are the spin curves that you see in the middle of the screen. So you have field thickness in the y-axis, and you have the spin speed in the x-axis, right? So the spin speed over here, it goes from 1000 RPM to 3000 RPM. And in the different colors, you actually have the spin curves for the different formulations of SU8 of this particular series, right? So you have SU82, SU85, SU810, and SU825, right? So you can imagine that one reason why spin coaters, they can start getting expensive, it's how accurate they are in terms of the spin speed, right? So you could have a spin coater that it tells you, well, it has a target value plus minus 500 RPMs. So for example, you say, well, I tell the spin coater to do 2000 RPMs, it might get to 1500 or it might get to 2500. Sometimes that might not be very important, right? But in some other times I can have drastic results. For example, if you take the red curve over here in the top where you have SU825, if you have a spin coater that it has a tolerance of 1000 RPMs, for example, then you can have a layer that it can go all the way from 33 micrometers all the way over here to 18 micrometers. That's a huge deviation on the thickness that you're trying to get in your layer, right? Now, that same spin coater might not have such an impact if you're only using SU82, because the curve for SU82 is relatively flat, right? You can go from, let's say, 4 micrometers to, let's say, 2 micrometers. Now, within the units itself, the percentage of error will be large, right? So always gauge what will be the impact or the spin coater on your actual process, depending on the resist that you're trying to coat. All right. Now, some processing trends in terms of spin coaters, right? So on the top left, you have the spin speed, you have the film thickness. In general, as you start increasing the spin speed, that thickness will start decreasing. Also, as you increase the spin time, the thickness will start decreasing, and more importantly, it will start stabilizing, right? So you can imagine that it will be ideal that you have a spin time that starts getting longer in order to have that curve stabilize and have a more uniform and reproducible thickness, right? Also, you will you will encounter different spin coaters design where it can be an open ball or a closed ball. So for example, over here on the top left, you have an open ball design. When you actually put your substrate, you start you put your photoresist, you start spin coating, and all the solvent that it's coming out during the spin coating, it will just evaporate into the atmosphere, right? So you can imagine that there will be a large gradient of the concentration of the solvent from the material itself to the atmosphere. Now you can have another design of spin coater called closed ball, where you have your spin chuck, you have your wafer, you put your photoresist, then you will close the lid and then you start spin coating. Right? In those cases, you can actually, in some models, you can actually control the exhaust volume, but you can imagine that in this particular design, the closed ball design, you have a much less gradient on the concentration of the solvent from the material itself of the photoresist to the atmosphere. That is good because the less gradient that you have, the less evaporation rate that you will have of the solvent, and that will allow you to have similar consistency of the photoresist during your entire spin coating process, right? The implications of that you can see here in this green curve. So you have the thickness uniformity on the y-axis, and you have the exhaust volume on the x-axis. So as you start increasing the exhaust volume, right, meaning that you go a little bit more into an open ball design, the uniformity will start decreasing. That is because you have that large gradient on the concentration of the solvent, right? So you can imagine that because of that large gradient, the viscosity of the photoresist, it will change throughout the spin coating process, right? Because the solvent is evaporating and the resist that remains, it will start getting thicker and thicker. So the uniformity will decrease, right? Now, if you start increasing the exhaust volume as well, the film thickness will start increasing because of the same reason, right? You will have more evaporation of the solvent, right? Then the resist will start getting thicker and thicker, and that's why you start getting a layer that it will get thicker, right? So in general, you actually want, or you should prefer, the closed ball design, because that allows you to have a more control on the atmosphere around the photoresist while you're doing the spin coating. That can lead to better uniformity, right, and better reproducibility on your results. Now, in terms of how the spin coating actually looks like. So over here you have a graph where the x-axis is the time and the y-axis will be the spin speed. So you can have two different kinds of pouring. You can have a static pouring where you put your substrate on the spin chuck, and then you will pour your material in, right? Or you deposit your material in before you start spinning. That will be static pouring. On the other hand, you can have dynamic pouring where you actually put your substrate on the spin chuck and then you start rotating or spinning a lot of speeds while you depositing your material on the substrate, right? So usually you go to 500 RPMs in order to do an initial spread of the material on the substrate, And then you will ramp it up to a particular value of speed, or x, as is shown here in the graph. And this x value will let you specify the thickness that you're interested in, right? Usually you stay there for 30 seconds, 40 seconds, right, in order to have that particular thickness. And in some cases, if you want to eliminate the EBR, one easier way to do it is to actually do a burst where you have the x speed that you were spinning at plus 1000 RPM in order to do a short burst and try to kick that excess material from the edge and eliminate the edge bead. After that burst on speed, you come back to the X speed for 5-10 seconds in order to stabilize before you actually start decelerating. Now, some other spin coaters, they can also get fancier when they actually shoot a particular solvent on the edge bead in order to dissolve it chemically, right? So if you have access to those, that will be ideal, right? But always measure what is your edge bead, what are the dimensions, and how it's impacting your process. Now, while it looks relatively straightforward, the spin coating looks relatively straightforward, there are a number of problems that you could encounter, right? So the film can be too thick, the film can be too thin, right? So in those cases, make sure that you check what is the viscosity of the resist that you're using, the spin speed that you're using, right? So you can adjust it accordingly. I was telling you more about the edge speed, but you can also have some of these problems that they're shown here in this slide. You could also start having air bubbles. So always be careful when you're pouring your photoresist on your substrate, right? That you don't incorporate air pockets during your pouring. So start pouring on one location and do not move, right? So just pour it in the center of the substrate, but don't start going like this, right? Because in those cases you are introducing all sorts of air pockets that it will derive into air bubbles, right? Meaning that you won't have a very uniform layer, right? And probably your process won't be as good as you designed it, right? You could also have comets, streaks, or flares. These ones are most common when you have impurities on the substrate. You didn't clean it very well maybe, right? Or also when you have some topography already on the substrate. The swirls, this is a very common problem with an open bowl design for your spin coater. So basically here, the layer of the solvent is evaporating too quick, right? And basically you froze the photoresist during the spinning process, right? So here you can see a really, really nice pattern of this swirl, right? Now the solvent evaporated prematurely, so now it's too viscous, and the centrifugal forces cannot move that photoresist anymore. Another very common problem is that of fingers. So in the case of the fingers, one reason it can be that you did not pour enough material, right? And another common reason is that your substrate is not well centered to the spin chuck, right? So basically, if your substrate is not well centered to your spin chuck, well, the centrifugal forces, they will start moving the photoresist in different directions. And particularly when you don't have enough material, you can have some parts of the substrate that they were not coated with the photoresist. In some other cases, you can start having pinholes, right? So meaning little pockets over here and little parts of the substrate that they were actually non-coated with the photoresist. So in those cases, always check your cleaning process and also check the quality of the photoresist itself. So sometimes photoresists that they have been sitting for long, right? The compositions, they might start changing and they might start leading to different problems on your process. Now, after you have that very uniform, beautiful layer on your substrate, now we need to soft bake it. We need to soft bake it in order to evaporate the solvent that allows us to do the spin coating. But we don't want that solvent when we do the exposure step, because when the photoresist still has a solvent, it's very sticky, right? So that can be very practical issue, right? And it's a very good adhesive, right? So you definitely want to get rid of that solvent. And also because by the time that we want to expose our photoresist with a particular wavelength, we want to have an homogeneous layer of photoresist. We do not want to have the mixture of photoresist plus solvent. Right? So in terms of the baking, so parameters of interest include the time, right? The temperature, the leveling of the plate, right? Because imagine that if the plate is not very well leveled, the photoresist is still fluid. So in those cases, if it's not level, it will start tapering on one way, right? So that can be a huge problem. You will also need to eliminate vibrations, because imagine that you have a hot plate that is just vibrating, right? Maybe not that much, but little vibrations. You evaporating the solvent, so you have the risk of freezing those vibrations into the photoresist. So instead of nice flat layer, you could actually have evidence in the layer of the vibrations, right? You also worry about the atmosphere, right? So whether you want to do it in oxygen, whether we want to purge it with nitrogen, right? All of these things, they actually have an impact on the quality of the layer that you will be exposing. The next one is quite important, and that is the type of heating, right? So you can imagine that you can put it in a convection oven, or you could put it on a hot plate. The hot plate will be preferred in order to remove the skin effect, right? The skin effect is when, imagine that you have your layer of photoresist and you are applying heat from the top or from everywhere, right? So if you start applying heat from the top, as in the case of a convection oven, for example, you'll start evaporating the solvent on the outer parts of the photoresist. And because you start evaporating the solvent from the outer part first, then you have the risk of developing a really nice crust around the photoresist that it will impede the evaporation of the solvent that is in the bulk of the photoresist. So a hot plate is preferred because the temperature or the heat will only come from the bottom, right? So if the heat only comes from the bottom, then you can prevent that skin effect. And also be worried about the temperature ramp. So how fast are you heating your photoresist, and also how fast are you cooling it, right? Consider, especially for thicker photoresist, these thermal gradients can actually incorporate stresses in the photoresist that will eventually show up later in the process, right? This particular table, it shows you some guidelines on the kind of the pre-bake, the soft-bake times that you can expect. All of these tables that they're shown here, you can actually find them in the processing data sheet of the SU8 formulation that you're using. All the providers will provide you with the processing data sheet. Now, after you do the soft baking, then it comes exposure, right? So now it is a time to actually expose your photoresist. Hopefully by this time it's an homogeneous layer of resist. You don't have any solvent anymore. So you will actually expose it with a particular wavelength, right? What is the goal of exposure? That will be to initiate a reaction, right? A cross-linking for a negative photoresist or scission for positive photoresist in the areas that are exposed to light of a specific wavelength. For SU8, usually we use 365 nanometers. Now, for a chemically amplified resist like SU8, you will expose and you will initiate that cross-linking reaction, but you actually need an extra thermal energy in order to finalize the cross-linking. So the exposure and the post-exposure bake time actually come hand on hand, right? In some cases, you can decrease the exposure while you increase the post-exposure bake, or you could increase the exposure while you decrease the post-exposure bake. So consider that this should be a product or a joint product in order to achieve cross-linking. And there are many parameters of interest in the case of exposure, right? So the first one, which you need to know what type of photoresist you have, positive or negative, so you can design the mask accordingly, right? This sounds easy, but it can be surprising to see how many times we might oversee that, right? So we didn't take enough care on designing our mask, and we end up with a structure that is actually the exact opposite of what we were hoping for, right? So be careful with that. So now then you have the type of exposure setup, so you can have shadow versus projection. You also have variations on the type of mask, so it can be metal on glass, it can be a printed film, it can be self-aligned, it can be conformal mask, right? So there will be multiple ways to actually obstruct the light in particular locations depending on the structure that you want to get. You could also have exposure only from the top, or you could also have exposure through the substrate if your substrate allows. For example, fused silica will be transparent to 365 nanometers, so you can expect to be able to do exposure through the substrate. You could also have inclined exposure in order to incorporate certain angles, right, in your structures. You have to worry about alignment if you're doing more than one layer. And you will also have to worry about the kind of illumination that you have. What kind of wavelength do you require? What kind of power do you require, right? And the uniformity of the illumination source. At the end, you're interested in delivering a particular dose to your photoresist. The processing data sheet, again, it will recommend particular doses depending on the thickness that you're trying to expose. And that dose will be given by the intensity or the power in watts of the light source that you have times the time of exposure, right? So that will be the time of exposure in seconds, right? So the processing data sheet, it will tell you the kind or the value of joules that you require to deliver to your layer. You will likely know the amount of watts that your particular power lamp delivers. So then you can calculate the exposure time and then you proceed accordingly. And also you have to worry about the resolution and critical dimensions in the pattern, of course. Now, so I was telling you, you had different types of exposure. So you can have the contact aligner, proximity aligner, or projection aligner. So in the case of contact aligner, as the name implies, so you have your UV lamp, you have your optics in order to improve the uniformity of the exposure, you have your mask, and then the photoresist will directly contact the mask, right? Remember I was telling you to make sure that you don't have solvent in that photoresist? Well, this is one of the practical reasons. If you still have solvent in your photoresist, that photoresist it will still be sticky. So once you bring them into contact, it will be a little bit of a disaster and a whole lot of cleaning that you will have to do, right? So be careful that you don't have that solvent anymore, right? You could also have another setup that is called proximity. So it's similar setup that in the case of contact, but we will actually control the distance between the mask and the photoresist. Still, it's very important that that photoresist is not sticky by any means, because usually most machines, what they actually do is that they actually bring the photoresist into soft contact with the mask, and then that will be the reference point, and from there they will actually retract the photoresist a particular distance depending on what you tell the machine to do, right? So in both cases, make sure that you don't have solvent in that photoresist before the exposure. And then the last one is projection aligner. So this is the case of a stepper where you actually have optics to have a uniform source of light. Then you will shine a mask, and then you will have another set of optics in order to gather all these diffraction modes, in order to focus them again into the layer that you're trying to expose, right? Then, depending on the setup that you have available, right? It's of course the setup that you will use, right? Some of them can be more or less expensive, and some of them they will have different resolutions, right? So for the next slides, I will be focusing on the use of contact aligner or proximity aligner. So in those cases, you can actually have two different kinds of masks. Two common types of masks are the ones pictured here. It can be a metal on glass, where you actually have a glass substrate that is transparent to 365 nanometers in our case, right? And then a layer of chromium, it has been patterned in order to generate the mask, right? So over here you can see the chromium on the edges and also the chromium in the particular patterns that you see in the center. You could also have a film that it has been printed with this opaque ink that it will block the 365 nanometers. So you can have that film, and then usually you'll tape it onto a harder substrate, for example, a glass substrate. And in both cases, you can see that you have regions that they are transparent through 365 nanometers and regions that they're opaque. So in these cases, you can actually pattern the light that gets delivered to the photoresist that you have underneath. And depending on the kind of mask aligners, they can be multiple options. Always checking your clean room, what kind of equipment you have available, what are the capabilities of that equipment. Sometimes you can do double-sided alignment, for example. Sometimes you can do bigger substrates, right? So always check on the kind of specifications of your equipment. In general, for all the equipments that they're pictured here, usually the smallest resolutions will be around 1 micrometer. So keep that in mind, right? So again, parameters of interest in exposure. So the type of photoresist, the exposure setup, the mask itself, the exposure side, top or through the substrate, the alignment, the illumination, and the resolution and critical dimensions in the pattern. Now, for the case of shadow printing, we will be working on the near field or Fresnel diffraction, right? So a practical equation that you can use in order to estimate the maximal resolution that you could achieve, it's pictured here in this rectangle, right? So you have the resolution that you're trying to achieve. Let's imagine, for example, that you want to have a 1 micrometer resolution, right? Then you start determining what kind of setup you actually require. So the gap between the mask and the photoresist, what is the minimum or the maximum photoresist thickness that you will be able to process with that resolution, right? So by plugging different values in this equation, you can quickly determine what kind of resolution you can get depending on the thickness that you're trying to achieve, right? And the wavelength that you have available to you, or on the other hand, have a resolution in mind and actually calculate what kind of parameters you actually need to have available, right? So remember that I was telling you that it is very important to have a uniform layer across the whole substrate, right? It is very important because if you don't have a uniform layer across the substrate, this C here, it will be changing throughout their substrate, and the resolution you can expect to change, right? So if you're really working on the borderline, right, on a particular process, and this C is varying a lot, you can imagine that the resolution that you can get in certain patterns will be different, right? So always keep that in mind. So far, I was telling you about the use of this mask in order to do conventional lithography, right? Where you either deliver a full dose of light or not light at all, right? So this is pictured here on the left image, where you have the regions in white that they get fully exposed, right? So basically, you have the whole thickness of the material that you wanted in the area or not thickness at all. There is an alternative called grayscale lithography, where instead of delivering either full dose or no dose, you can actually incorporate a grayscale, right? So for example, in the case of SU8 that gets exposed from the top, you can see over here that you have the original layer that you spin coated and baked, right? But thanks to the grayscale mask, you can vary the exposure dose depending on the location. So the one on the left, it gets exposed with the full dose, right? The one in the middle, it's more like a third of a dose. And then the one on the right is more like a 2/3 of a dose. So after you do the post-exposure bake and you do your developing, you can actually aim to have structures that look like this. When you don't have only zeros and one, as in the case of conventional lithography, but now you have different thickness incorporated and all from the same layer, right? So this is a very interesting capability that it can be useful in a number of applications. So one way to incorporate this grayscale lithography, it's using the DLP technology. So you probably have heard of this DLP technology when you have an array of mirrors, right? And depending on the switching rate of the mirrors is the kind of light that you will deliver to a particular screen. I'm pretty sure that you have had maybe some TVs or that you have actually experienced this from some of the projectors in your classrooms, in your homes, right? So consider that by using this array of micromirrors, you can actually develop different intensities of light into the photoresist. So for example, in the rightmost curve, you have the grayscale value in RGB in the x-axis. So it goes from 0 to 255. So remember, 0 will be black, 255 will be white. And then you have the exposure power in milliwatts per centimeter square in the y-axis. So when you have a 0 RGB value, you don't have really an intensity, right? While you have 255, you can have the maximum intensity in the light, and then you can see all these values in between. So by actually choosing your RGB value in the mask, and this is a software mask, by the way, right? So you don't need to have those physical masks. It's just a software mask and a light that gets shine into the photoresist, right? So once you have that, then you can imagine that you can start having the structures like the ones that they're shown here. So the case for A, it is in particular the photoresist was actually exposed through the substrate, right? Over here, well, actually in the case of A, B, and C, all of them, they were exposed through the substrate. That's why you see this particular pattern. In the case of D, this actually was exposed from the top, where the anchors here of the post, they actually get exposed with full dose, and the little bridges in between, those are the ones that get exposed with partial dose, right? And you can find more details in this particular paper. This particular paper is a work that we did back in IIT Kanpur a little bit more than a decade ago, right? So you're encouraged to actually check it out and reach out to me if you have any questions. Now, you have the post-exposure bake. After you do the exposure, remember that basically you shine the regions of the photoresist that you want to keep. You will shine it with a particular wavelength for a particular time. You initiate a cross-linking reaction. So now is the time to provide an extra thermal energy in order to finalize that cross-linking reaction. So the parameters for the post-exposure bake will be the temperature, right? So the time of the baking, and very, very importantly, the heating and the cooling rates. So now the heating and the cooling ramps, they take a little bit more importance, especially for thicker photoresist, because if you're not careful with those, you can start stressing the SU8, and those stresses, they will actually show up after the development or during the carbonization. The type of heating does not matter as much anymore, right? So it does, since you don't have to evaporate solvent anymore, you could do a convection oven or a hot plate, right? So there's not such a high impact anymore. Now, remember that the exposure and the post-exposure bake come hand in hand, right? So the values that you get on the processing data sheet, they are the guidelines, right? But in some cases, you might benefit from actually decreasing the exposure dose, but make sure that you increase the post-exposure bake. So that will be a way to optimize and to achieve cross-linking. You are looking to actually cross-link the photoresist appropriately, such that it sustains the development, right, and it carbonizes well, right? So now during the post-exposure bake, well, this is more about the exposure actually. So when you're doing the exposure, you can imagine that you will suffer from diffraction, right? Especially if you don't have a very close contact between the photoresist and your mask. Most of the time, we do not want that diffraction to happen, because then it can lead to something sometimes called T-topping, where you actually have cross-link material on the top, and that will affect your resolution, right? So you can eliminate the diffraction by doing hard contact, right? You could also eliminate it by incorporating a filter on your mask aligner and making sure that only the 365 nanometer wavelength gets through, right? And while usually we are trying to fight the T-topping and eliminate it, right, such that we can have a high resolution or a good fidelity on the patterns, sometimes you could also use it to your advantage, right? So here are two particular references where we were studying how we can actually use this diffraction in order to incorporate suspended bridges, suspended wires, right? So it all depends on the distance between the patterns themselves and also the geometry of the pattern. Whether they're two flats facing each other, like in the case of the squares, or 2 points facing each other, as in the case of these diamonds, right? So depending on that, you could actually start determining whether you get a plate or a bridge, or you can start getting a wire, right? So that could be another way to leverage the diffraction, right? So you worry about the gap between the anchors, right? And also the gap between the mask and your photoresist layer, right? So again, I encourage you to check these two different references, and if you have any questions, feel free to reach out. So towards the end of the process, now we have development, right? So in the case of development, we will have a particular chemical that it will attack that particular photoresist. So the choice of developer is usually tied to the resist use, right? So here you have some examples for positive photoresist, some examples for negative photoresist. In the case of SU8, we will use PGMEA, sometimes also sold as SU8 developer, right? So in these cases, take care that you're using the right chemical, of course. Also, you consider how friendly is that chemical, right? So whether it's organic versus water-based. And in terms of processing, whether you're going to immerse the whole wafer into a bath of that chemical, or if you should be doing only spraying, right? The time of development, it will be very important. The time of development is really, really important in the case of positive photoresist, because you have a high risk of overdeveloping your resist and impacting the resolution. Remember that the positive photoresist, when we expose, we only weaken those areas that we expose, but we do not strengthen anything else, right? So you can imagine that that chemical, if you leave it in contact with too long with the photoresist, it will of course etch the photoresist that was weakened, but then it will start deteriorating the rest of the photoresist as well, because we did not cross-link it, right? In the case of negative photoresist, we will be less prone to do that because we actively cross-link the photoresist, right? And then in terms of the temperature, sometimes you actually want heating in order to increase the rate, right? And sometimes you also will desire agitation in order to refresh the developer across the area of interest, right? And sometimes even you might want to incorporate sonication in those cases when you need to develop very intricate geometries, right? So where the gaps are very small, such as the sonication, they can actually refresh the developer in those very small areas. After the developing, you will rinse and dry. So basically, you will start replacing the developer with something with different chemicals in order to facilitate the drying, right? So it will be common to replace the developer with lower surface tension liquids, just like IPA, such that you can then spin dry or blow dry, right? So always check the surface tension of the particular solvents that you're using. You want to reduce that surface tension with respect to the substrate in the SU8 in order to facilitate the drying. Sometimes you might actually require critical point drying if the risk of sticking is important, because you don't want to end with a feature that looks like the one that is in front of you. In these cases, so the photoresist, it was exposed correctly, right? Maybe it was not baked for long enough. Maybe these posts, they're not fully cross-linked, so they're still quite pliable. And when you're actually trying to dry it, the stiction that develops between the posts because of the liquid leaving the substrate, that will cause these posts to actually come together. And once that happens, that's a failure in most cases. Some colleagues, like Dr. Wang, actually has used this in order to create different patterns, right? So it all depends on the kind of structures that you're aiming for, right? But consider that when you're drying, you actually need to minimize stiction such that those features, they stay in place. And then at the very end, then you have the option. Either you hard bake it, or you remove it, or you do nothing, right? So I personally recommend for the CMEMS application to actually hard bake, right? So after you do your rinsing and your drying, you can actually hard bake from 15 to 20 minutes at 200 degrees C. So this will improve the strength of the pattern itself, and it can also improve the adhesion to the substrate. So this was particularly important when I was using fused silica. So when we have fused silica, that hard bake, it seemed to have a crucial effect on whether the SU8 paralyzed well or not, right? So that will be something for you to consider. And at the end, you can end up with features that look like this, right? So this particular structure is basically two processes of photolithography. The first process to create these planar structures, right? And the second process to put these posts aligned with those planar structures, right? So if everything goes okay, you should be having something similar to the design that you were looking for, right? So here are some selected references. So again, these are just a few. Some other authors that you want to check out. It's Mark Madu, Chunlei Wang or Peggy Wang, Stefan Keller, Sam Kassen, And most of them, they will actually be talking to you in future presentations, right? You can also have more links available at this particular website. So this is my research website. So you can have links to all the papers in this particular site, right? So with that, I would like to close this particular processing approach. Remember, this was a photolithography in order to create the precursor to the carbon, right? So after we get these photoresist structures on a particular substrate, then we will actually go and put them into the furnace, right? We put them into the furnace, we will heat treat it with a particular ramps, as you will be seeing throughout this summer school, right? In order to create the carbon that we're interested on, right? So depending on the application, you can have different structures, different dimensions, also different treatments onto the surface of the carbon, and different colleagues, they will actually talk to us about these variations in the process in order to achieve a particular functionality, right? So stay tuned for more presentations, right, on how you can actually start incorporating improvements and optimizations in order to derive a whole bunch of different materials that can be used for many different applications, ranging from capacitors to neural probes, scaffolding for cell culture, electrophoresis, and so on, right? So with that, I'll close this particular segment, and I will see you just in a little bit more.